I'm sure all of you by now are very well aware of plastic deformation, right? In strength of materials, we have covered that in detail, theory, numerical part, lot of things we have discussed, which was relevant for strength of materials. It will be coming again in manufacturing and production in metal forming, which we will cover after this subject, right? Currently, we are studying material science, then metrology, and then we'll move on to manufacturing and production. There again, it will be coming plastic deformation in the unit of metal forming. But before moving to that, here, right now, I am going to talk something about plastic deformation because in material science, we are going to discuss that in detail. Yes, in material science also, we have to cover about dislocation theory, which talks about plastic deformation. Next unit, we are going to do that. So you see a single topic of plastic deformation, but different parts of plastic deformation, different aspect of plastic deformation, we cover in different subjects. That's the connection between all the subjects. So up to this point, in this unit, we are studying about the structure of unit cell. Atoms, how they are arranged in the unit cell. How closely or how tightly are they packed? What are its different types, right? All these things we are studying so far. Basically, the structure of it. But how that structure is going to deform and cause the plastic deformation, that we are going to study in the next unit. But it depends upon the structure. If you recall, in the same unit, we have talked about atomic packing factor, APF, which was telling us how densely the atoms are packed in a unit cell, right? Kind of density, how dense the material is going to be, how many atoms you have packed in a given volume, and actually that decides the volume, the density of the material is decided by how closely packed, how densely packed the unit cell of that materials are. So that density is not the only type of density we have. There are two more type of densities that we are going to cover in this lecture, which is called as planar density and linear density. Planar density and linear density. That was a volume density. Atomic packing factor was volume density. No? We were talking about in the volume of unit cell, how much fraction is packed with atoms. That was for volume. But same type of study we are going to do for a plane as well as for a line. That in the cubic cell, along a specific plane, how much area is covered by atoms. That if you cut a specific area in a cubic cell, how much percentage or how much fraction of that area will be having actually atoms and rest would be void. I will be discussing that in detail. I'm just giving you a broad idea right now. Similarly, along a line, if I draw a line, direction vector, right? Again, we have studied about the direction vectors in crystal lattice structure. So, along a direction vector, how much portion of the line will be covered, will be passing through atoms? That will tell us the density along a specific line. So, you see where we are going with this, where this direction will lead us in the next unit. That when atoms are going to deform, or not atoms are going to deform, the layer of atoms is going to dislocate. That will cause the deformation. But along which direction it will deform, that will be decided by how much densely packed that direction is, or which plane will get deformed will be decided by how much dense that layer is, that plane is. That's the significance of knowing about these two type of densities. So far I was just giving you an idea of what we are about to study and why that study is important. Its actual feel you will be able to take in the next unit. But still, it's very important from the point of view of understanding also, because without this proper understanding of next unit would be slightly difficult, as well as from the point of view of numericals also it is important. Because numericals can be asked and some tricky question can be framed. So I will be discussing that. I will be discussing about I'll give you a tip also in this lesson. I'll talk about a silly mistake also which is possible, or you can say confusion that some students can have in this topic. So make sure that you understand it clearly. So firstly we'll talk about planar density, which tells us, you can see the formula. The short form of planar density is PD. It is denoted by PD. It is also sometimes called as just like we have atomic packing factor, which we have discussed atomic packing factor. In a very similar way, this is also called as replace atomic and write planar packing factor. That is also a name which is used for this. Sometimes a planar packing fraction is also said. Okay, these are the different names of this parameter. It is denoted by PD, as I told you. So what does it tell you? It looks very similar to APF. Only difference, volume is replaced by area. There we were having that out of the total volume of unit cell, how much volume was occupied by atoms. Here it is out of any given area. Any given area means we can take this area also. We can take maybe this area also, this area also. You see, it's the diagonal area. It is the diagonal area, right? So along any crystallographic plane in this unit cell, that area will be coming here. So in that area, how much area is occupied by the atoms? So if you draw a rectangle over there, or hypothetically you cut it, so how much area would be covered in that plane? How much area, fraction of area would be covered by atoms, and rest would be void. So this is what it tells you, that you're getting the feel now that along a plane how much closely packed the unit cell is. And there can be many planes. There's not just one plane, right? The APF was single. There was just one value of APF for a specific type of structure. For example, this is the BCC structure that I have shown, right? BCC structure. So for BCC we were having a single value of APF, but planar density can be different. Why? Because depend karta hai which type of plane we are going to choose. Are we going to take this plane, that plane, diagonal plane, or we are going to take this plane, right? 111 plane. This is called as 111 plane, right? You remember? We have discussed this in the last few lectures. So what type of plane are you taking? That will decide the area of that plane and how much fraction of that area is occupied by atoms. So it will be different for different planes. That is why the way we represent this has a subscript also of that plane. For example, if I want to know the planar packing density or just planar density in a 110 plane. So this is how I am going to write it. In subscript, I will write the notation of that plane. There's one more way to represent that, where we will write this, then along which plane are we talking about, and then we will write the type of packing, whether it is BCC or FCC. So these are different ways in which the planar density can be denoted. Now, let's understand how to calculate its value. So let us take an example. The best way to understand this would be to take an example. As you can see, this is the BCC structure that we have taken here. And in this BCC structure, let us take 110 plane. Let us take 110 plane. So how it's going to look like? This is going to be 110 plane, right? If you remember, we have already discussed about these, and we are going to discuss even more things about this. So it's very important for you to know these basic things. Anyway, so this is the plane which we are talking about, 110 plane. Correct? It's passing diagonally, right? If I show that plane to you here in this diagram, then this is how it is going to look like. This one. E is at the center. Here also you can see E is here at the center, and A, B, C, D. Then this is A, B, C, D. Very careful in the geometry. Very careful. Which atoms are touching each other? It's very important to know. Don't do a mistake of touching A and B in this, right? Or don't do the mistake of touching A and D in this. Why? Where do they touch? You remember all the types of structure we have discussed. So you need to be very careful that in BCC, it is the central atom, the body center atom, which will be touching all the corner atoms. That will help you in the calculation. You will see it very soon. In APF calculation also, that was deciding that which of them are in contact, direct contact with which atom. So this is a very small but very important thing to note to avoid any type of mistake. Anyway, so here this is what we have. The thing is, the planar density is that if you look at this area, or in this diagram this area, how much percentage of that area, how much fraction, not percentage, sorry, not percentage, we are not multiplying it with 100, how much fraction of that area, this area is actually covered with atoms, is actually occupied by atoms. So if this entire area, you see this portion, then this portion, then this portion, right? All these portions you can see are actually covered with atoms, and then there are voids also, right? In this, let me take the black color for this. So in this, you can see in this area, there are certain voids also. This is a void area, void area, void area, void area, and some area which is occupied by atoms also. So out of the total area of that plane, how much fraction is covered? This is what visually it is showing you, right? I know you understood it. I am not repeating it. I am just telling it from the point of view of different diagrams. This I explained, then this I explained, now I am coming to this. So in this area, how much fraction is covered by atoms? This is what this planar density is telling you. So how do we calculate this for BCC 110? Let us see that. Let's apply, let's put the values in this expression. So we know that you firstly notice this thing. What I told you, that how it can be denoted, right? Planar density of 110 for BCC. So here area occupied by atoms can be broken down into how many atoms you have and how much is the area of one atom, right or not? Total area occupied by atoms, how much it will be? At area of one atom multiplied by how many atoms you have. How much is the area of one atom? Area we are talking about. What area? Not the curved surface area. Don't write the curved surface area of sphere. That's why I focused on this specific diagram. Don't think, oh, this one is at the center, so I'll take 4 pi r square as the curved surface area. No, we are not talking about the volume. We are talking about the area. You cut it, and now you are noticing, you are observing how much is this area, how much is this area. So we are talking about area of circle, pi r square, right? Planar density, area we are talking about. So here, how much is the area of one atom? Pi r square. Multiplied by how many atoms you have? Divide by how much is the area of that plane. Which plane? This plane, whatever plane it's going to give you, it will have different area. Question may choose to give you any of the planes. So many planes are there. So depending upon that, the denominator value will be decided. Okay, one by one we'll see that. Firstly, we are focusing on here, number of atoms. How many atoms do we have here? Very easy. Notice how many atoms do we have. This is one full atom we have, right? And then this is 1/4, 1/4, another 1/4, another 1/4, another 1/4. So we have one full atom plus 4 atoms which are 1/4. So cancel 1 plus 1, 2. So we have 2 full atom area, cross section area here. That's why number of atoms here is 2. We have 2 atoms multiplied by area of one atom, which is pi r square. Divide by area of plane. Which plane? 110 plane. In BCC, 110 plane. Now let's find that out. I would like you to pause the video and try to find that out, because we have already discussed about APF. So I think you can try that, you will be able to do it. So for this plane, 110 plane in BCC, the area of plane, which is a rectangle, will be given by one dimension multiplied by the other dimension, AD multiplied by CD. How much is AD? Let us say small a is showing you the edge, right? A in a cube represents the edge of the cube. So that's what A is. This is also A, this is also A, this is also A, right? So this A, which is AD, multiplied by CD, this is CD, diagonal is CD, right? So if you look at it from the top, this CD, if you look at it from the top, this is the top view, huh? If you look at it from the top, so that is C. Bottom area I am looking at, huh? Because if you look at the top, B is above C. So actually you will have a look at B. But we are talking about the bottom plane, CD I have, that's why I have written CD. AB also you can take. Length is same, yeah. It's a cube, na. AB also you can take. CD also you can take. Here you can write AB also. What is the issue? No issue. Length is same, right? But since I have written CD, so I am looking at the bottom area. So this is C, this is D, and this point, let's say it is F. Okay. So this CD is the length that we are trying to find out. Okay. This FD is A. This CF again, it is A. So how much would be this diagonal? Pythagoras, root over A square plus A square, which is A root 2. This is 90, right? These are cubes. So CD is going to be A root 2. Multiply them, you will get A square root 2, right? So in this expression, where we have to find out planar density, AP value we have got. So what's the issue? Can we just put A square root 2 and that's what our answer will be? Can I just put here 2 pi r square divided by A square root 2 and I call it to be the planar density? No. Because means I can, but that's not the standard way. Why? Because there's still A and R left which have some relation between them, right? You will simplify, no? Any expression you have been given, anything question is asking you and you are getting 4 by 2, what you will say? Answer is 4 by 2. You know, you will cancel it and you will write 2 is the answer, right? So in a similar way, R square and A square, they may look very different to you because they are different alphabets, A and R. You cannot say that R got cancelled by A and I have got 3, right? You cannot do that. But they are related. There is a relationship between them, which we will be able to see from this diagram, right? And this is what we have done in APF, in atomic packing factor, right? This relationship, that's very important actually, because again, how the atoms are connected to each other, which atom is touching what atom. If you will do mistake there, gone. You will not be able to answer such questions. So you should be very clear that in FCC, what atom is touching what corner atoms. In BCC, if corner atoms are touching each other, if center atom is touching which atom, all these things you should be very clear. If you are able to visualize it, if you know it, you will be able to solve whatever they are going to ask. So here, what we are going to do, we are going to establish the relationship between A and R. That will help us in putting the value here and getting the answer. So relationship between A and R in this, how is it going to be? A is this, A is this, A is this. But they are not touching each other. Yahan to gap hai, there is a gap between them, right? This is A. But I cannot say A is equal to 2R because these two atoms are not touching each other. There is a gap. There is a gap between them, right? This is R, this is R. So A is definitely more than 2R, but it's not actual value you cannot find out from the edge. Always whenever you are trying to establish the relationship between A and R, always remember this tip. Look for the line which is continuous, where one and other atom are continuous in touch with each other. There is no gap, there is no void. Because you know the dimension of atom, right? R, 2R, we know that dimension. We don't know the dimension of gap. We don't know the dimension of that hollow void. So you have to look for that line along which atoms are just connected to each other without any void. Here, this is going to be that line, right? Again, this is something we have already discussed about. That atom, corner atom, then center atom, then the other diagonally opposite corner atom, right? This atom, this one will be touching this center one and this is touching this one. So these three atoms, this, then this one and this one. They are in a straight line connected, right? So straight line we are looking for because it's easy to apply the geometrical formula for a straight line. So in that straight line, how many radius are coming? This one entire thing is coming, which is equal to 2R. Then 1R here and 1R here. So 2, 3 and 4. 4 radius are coming in that line. Means BD is equal to 4R. BD is equal to 4R. Right? This is true for BCC. BD is equal to 4R. And this BD now you have to write in terms of A. How you can do that? Again, very simple. Look at this right triangle. Again, it's a right triangle, right? This triangle I am talking about. This triangle. Basically, it is the half of entire plane. This plane we were having, na? You just cut that in half. You just cut that in half from here. From here. So you are going to get a plane, na? So that is the plane we are talking about right now. Hai na? So in that plane, what we are going to do, in that plane, right plane, this BD, you can apply Pythagoras theorem from the geometry, right? BD square is equal to BC square plus CD square. How much is BD? BD is equal to 4R. So 4R whole square is equal to BC. How much is BC? It is A square. Plus how much is that CD? So CD is A root 2. A square and then Pythagoras, right? This one, CD is how much? A root 2. So that A root 2 we are going to put here for CD. And then you just simplify it. This is 16R square is equal to A square plus 2A square, which will become 3A square. So this gives us A square is equal to 16R square by 3. So you see now the relation between A and R, which were looking unrelated, but they are not. So A square is equal to 16R square by 3. This you are now going to put here, right? And then R square are going to cancel out. So that's what now we are going to do. Putting it back in the expression is going to give us this, right? AP was there. In place of AP, we have written A square root 2, and A square value is 16R square by 3. So 16R square by 3 root 2. Got it? Now you just have to simplify. This was A square, है ना? So R square cancels R square, and here what will happen? This will cancel it. It will become 8. 3 will go in the numerator. This is what you are going to get. Correct? And if you put the value, we know the value of pi obviously. So if you put it, I think 0.833 is the value you will get, right? So 0.833 is the planar packing factor or planar density for BCC along this plane. So it gives you an idea of how densely packed that plane is. Similarly, you can find it out for different planes, for 100 plane, for 111 plane, and you can see which plane is most densely packed, and that plane has the most tendency for dislocation because that's most tightly packed. I'll discuss that. There's some very interesting thing which we are going to discuss in the upcoming lectures. Now, before moving to the linear density, which is very similar to this, let me give you a caution here, a possible blunder, mistake, confusion in the formula. This is the formula of PD that we have covered. But there is one more formula for this, which you will be able to see depending upon different sources. Which denominator is the same? How much is the area of the plane? But in the numerator, you don't have the area of the atoms, but you have number of atoms. Number of atoms on that plane. So that is also one more way in which it is defined. Number of atoms means here pi r square will be gone. This will be gone. This will be gone, right? So obviously here you cancelled a square r square, right? Having the relation between them. But that you will not be able to cancel now. This will be only 2. So when you will put the value of a square here, which was in terms of r 16 r square by 3, when you are going to put it here, so it will be in terms of r, means 2, 16 r square, 3 will be in the numerator, this is going to be root 2, this is going to cancel 8. So this is what you are going to get, 8, 3 divided by 8 r square root 2. This is another way in which this value can be defined, which is in terms of r square. Both of them are used depending upon which source you are referring to, right? Many standard books, some of them use this formula, some of them use the other formula. But this is more standard, right? If a question comes in GATE about the planar density, obviously you can have a look at the options, or if it is NAT, so it will have to give you some value, right, of R. If they want you to put the value, use the other formula, they should give you the value of R. If they are asking you about the planar density, and it's an NAT question, that planar density for this question only, for BCC along 110 would be how much? So obviously this formula needs to be used, na? How can you use the other formula? How can you use this formula? Because this formula will have r square in the denominator, as I just showed you. So if question comes in GATE, you will have to analyze the question and see what it is asking you, right? Which formula would be suitable to apply. Having said that, this is the more general, more standard formula out of the two. So you need to be careful about this. In a very similar way, just like we have covered about the planar density, we have linear density also. I'm quickly covering it, which just tells us that if any length you select, any length, any directional vector, right? We have discussed about the different direction vectors in a unit cell. So suppose 110 you have selected, 110 you have selected, 100 you have selected. In that direction, if you draw the direction vector, how much portion of the line is covered, is passing through atoms? That ratio, that fraction will give you the linear density. Very simple, very similar to what we have been doing in APF and planar density. There APF was about volume, total volume ka how much fraction volume is covered by atoms. Planar density was about of a given plane, how much fraction is passing through atoms, covered by atoms. Here it is about line, any direction vector you are drawing in this crystallographic plane. So in that line, how much line length will be passing through atoms? Very similar to that, right? And this is all the parallel planar and linear densities. Both of them are going to have the significance in deformation, in dislocation, that along which direction it is going to dislocate. That will be decided by which is the most tightly packed direction, where linear density is highest. Similarly, where planar density is highest, so that plane will have the most tendency to dislocate, to cause plastic deformation. So this is the physical significance of having a high value of planar density and linear density. A quick example here, you can see that along this line, I have shown just these two atoms, N and M, right? Between them, we are going to analyze what is going to happen, N, M, and M. So you can see this is, how much is the length? A is the length, A is the length, है ना? Edge is A, right? So out of that A, you can see some portion is void, but some portion is covered by line. So this green part is covered by line, and let's say this blue part is void. So out of total length, how much fraction is green line? That's what this LD is going to be. This is also defined in a very similar way. Like we were writing atomic factor, atomic packing factor, we can write linear packing factor, another name for this. Linear density is also written as LD, as I have written here. It is also denoted like if you are writing it along 110. So you have to write LD 100 for what type of structure? This is body center, so BCC. Right? So denotation is same. So here, how much area you are covering? How much is the length occupied by atoms? Think. How much length of A is occupied by atoms? Are 2R. How much is this length? R. How much is this length? R. So how much is the total length occupied by atoms? 2R. And how much is the length of vector? This vector A, right? So for that, I am coming back to this BCC diagram, right? Here we have done that already, no? A square is equal to 16R square by 3. A square, this A, and this radius R, right? R is same, whatever R you take. So what is the relationship between A, this length A, and this radius R? That we have already done here, right? It tells you that A is equal to 4 by root 3 of R. If you take the root of this entire part, you will get A is equal to 4 by root 3 of R, right? For BCC, that's what we have from here. 4R by root 3. What's going to happen? R cancel. Root 3 in the numerator. Root 3 by 2, right? This will be cancelled. And root 3 by 2 value will come out to be 0.866. So that's the answer. That's the linear density along 100 direction in a BCC structure, BCC crystal. So these are the two topics which have relevance of concept, which we are going to discuss in the next unit, as well as these can be asked, PD and LD questions can be asked just like we have APF questions in GATE and other exams directly.